Recently, a link on the internet led me to the portfolio of Adam Heslop called Pixels in Progress, and amongst many other amazing things I found this artwork. And after fiddling around a bit, I figured a way of recreating something similar in Houdini. And what we're going to talk about in order to recreate kind of this increasingly subdivided artwork are for loops, for each loops, and a rather efficient way of rendering splines in Houdini. So let's get started. First thing I'd like to drop down is a geonode, dive in, and what I'd like to do is delete the standard geometry and add a volume. Because the thing I'd like to create first is a regular triangular grid, and the easiest way I found in Houdini to do that is by abusing a volume to do so. And I'm going to give it a size 4 by 4 and make it 0.1 units high, and give it a sampling by size, and the division size is 0.1, so that what we create is just one thin slice of voxels. Set its initial value to 1, and the next node I'm going to use is the points from volume node, which is set to 0.1 spacing already. And what it does in its standard settings is just scatter the points like in a regular grid. However, we can choose tetrahedral as a point configuration, which will give me initial points for a regular triangular grid. And all I have to do now is attach a triangulate 2D sub to it, wire it up, highlight it, and voila, we have a triangular mesh, which is, except for the edges, quite regular. And as our operations are only happening in the middle and the center of this grid, that's fine for us now. When looking at the artwork that we want to create in the end, it becomes obvious that what is happening here is we take individual triangles and subdivide them over and over again. So we subdivide them multiple times, and the variation that results in the pattern comes from different numbers of subdivisions for each individual polygon. And in order to drive those individual subdivisions, we need to give each polygon an attribute. So each triangle needs to have an attribute that tells my algorithm how many times the triangle should be subdivided. So let's create that. I'm going to use an attrib create for that. And what we'd like to create is a primitive attribute, which we'll call maxiter for maximum iterations, and we'll set this to 0 at the moment. Also, it doesn't need to be float, it can be integer, as we'll just count iterations, so 1, 2, 3, 4, 5. We don't need any floats for that. So now each of my individual triangles has an attribute of 0, so it gets subdivided 0 times. I want to drive that, and I want to drive that in a controllable way. So what I'm going to do is first create a sphere, set it to polygon, and let me highlight that, and dial up its frequency, maybe dial down its radius a bit, just a tiny bit, and on that sphere, the thing I'm going to do is just copy this attrib create node, wire it up here, but instead of giving it a value of 0, I'll give it a value of 4. So what I'd like to do next is transfer those attributes from the sphere onto my grid, and also fade out those attributes with a distance where the grid triangles move away from the sphere. So the way we're going to do that is with a node called attrib transfer. Wire up the grid on this slot, and the sphere on that slot. Over here, highlight it, and just goes to the sphere. And what I'd like to do is set up the conditions so that drives how the values get blended here. And one way to visualize the actual values that each primitive has, we can set up a visualization for that. We do that by right-clicking on the visualization icon, and within the scene we add a visualizer. And it's going to be a marker for our case. And the attribute we'd like to visualize is the max iterations, called this. close that. And now we see that with our current setup, when we highlight previously, every triangle had 0 iterations because we initialize it like that. But after the attribute transfer, suddenly each triangle has 4 iterations, and that's not what we want. We want those triangles very close to the sphere to have a max iteration value of 4 while fading out slowly till they become about 0 here. And the way you drive those is with these conditions. So the way they work is basically like a kernel, which we're going to talk about in another video. But it's similar to a blurring operation or to a sharpening operation. And these values drive how the values get transferred from one geometry to another and how they fade out and how far the geometry influences the transferred attributes. And by trial and error, I found out that these values work for my case. So what I see now is within here, very close to the sphere, I have maximum iterations of 4, and they fade out slowly over 3 to 2 to 1 to 0. The next thing I'd like to do is switch off the visualization and add normals to this. So I'm gonna use a normal node for that, like that. Okay. So what I have now is a regular triangle grid with attributes that tell my algorithm that I'm going to build now how many iterations of subdivision each of those triangles should be exposed to. In order to subdivide each individual triangle an individual number of times, we actually need 2 things. And those 2 things are 2 loops. On the one hand, we need a loop that individually separates each triangle, and another loop that runs a given amount of times for a given number of subdivision on that individual triangle. So the first loop we're going to build is the one picking out individual triangles, and it's called a for each loop. We'll do that with a for each loop here, and that automatically creates this construct. So it has a beginning and an end node, and in between we can put all the subs, all the nodes that we like to be executed for each individual piece here. Okay, let's wire that up. Within the begin node, I don't need to change much, but for later purposes, I need some data that's happening within this for each loop. And the way I can access this data is by clicking on Create Meta Import Node, which creates this third node here. And we'll have a look at that just in a second. In the end node, I need to tell the for each loop how to actually split the geometry into different pieces. And the way I want to split them for this case is I want to split them by their different iteration numbers, so that I can split them into a given number of pieces, and on the piece with the number of 1, I just run 1 iterations. On the pieces with number 2, I run 2 iterations, etc., etc. The way I'm going to do that is with the piece attribute, which usually takes the name of primitives in order to guess which primitives belongs to which piece. In our case, it's called the max iterations. So this just splits it into different parts for each individual max iteration number. Okay, let's have a look at the metadata node. What the metadata node allows me to do is access the data of this for each loop. So when we go into the geometry spreadsheet and go to the detail, we can see those attributes that the metadata node provides me with. And they are quite useful. For one hand, the number of iterations gives me the maximum number of iterations that this whole construct will run through. So this will run through itself a maximum number of 5 times. And this one here gives me the current iteration number starting from 0. So this is the last iteration, although it says it's got 5 iterations, which is exactly what it does because it starts from 0. So we have 0, 1, 2, 3, and 4, which are my 5 iterations. This is one thing you should get used to, because in computer science, you often start counting from 0, and the 0 is actually the first iteration or the first element in a given piece of code or piece of setup. So that is one thing to be cautious of, and which led to many errors when I started programming. So this was a constant source of frustration for me. So just keep in mind that in these nodes, in these loops, the first iteration is actually the 0th iteration. Okay, what I have now is a construct which splits my geometry, which splits my grid into 4 different pieces, or actually in our case into 5 different pieces. So from 0 to 4. And what I want to do now with those pieces is individually subdivide them a given number of times. In order for that to work, I need a for loop. I'm going to create that with a for loop here, and this looks pretty similar to the for each loop, with the only exception that I can tell it a fixed amount of iterations it should run through. And we're going to hook that up into the for each sub, like that. And what we're going to do is, in the end block, which is highlighted here, tell it to have a given amount of maximum iterations. So it will stop as soon as it reaches this number of iterations, even if I have a higher number of iterations input up here. This will always be regarded. So if this is lower than, say, 10, maybe I set this to, say, example 4, it will only run 4 iterations. So anything that I put in here will be run as many times as I have iterations here. Sounds a bit complex, but let's just keep building this, and I think you're going to realize what we're doing. Okay, what I did now, within the first for each node, I split my geometry into pieces. And each of those pieces has its individual max iteration numbers. And what I'd like to do is run this for loop the same amount of max iteration numbers that I have in the current piece that's in the for each loop here. And the way I'm going to do that is by accessing this node's detail attribute, and I'd like to access its iteration attribute because that gets increased for each piece that the for each takes out, and I just want to feed this attribute into this max iteration slot here. And the way I'm going to do it is with a small expression called detail, and this will extract a given detail attribute. And what I need in order to extract that attribute is to point it to the node where it should get that attribute from, and this is this node in our case. And I'm going to do that with this syntax. So this is a path like a file path in a browser or in a Unix terminal. I'll input 2 points, which means go up 1 level. Go out of this node, leave it. And then Houdini offers me an autocomplete here. And what I want to point it to is this for each begin metadata. So just going to go down here. And it is this node that I want to point it to. So just as a file path, I'm going to go up 1 level and point it to this node. That's happened here. The second thing my detail expression needs to know is the name of the attribute that we want to access. And I'm gonna type a comma here and give it quotation marks, and the name of the attribute that we want to access is called iteration. Like that. And the last thing it needs is a default value. So if it does not find this attribute, or if there's any mistake finding it, or if there's something wrong, just use this default attribute, and I'm just going to use a 0 here. So now this loop automatically runs x times and x depending on which piece we're working on. Okay, now what we need to do, or what we want to do originally, is just extrude a given polygon inwards, and we're going to do that with a poly extrude node. And we'll just wire up that in here. And let's go to the scene view again, and maybe add a null at the end of this loop and highlight it. So we see nothing much happening here. That is because within the extrude node we haven't set up any extrusions. So let me just pull that down and go to spline control and dial down this end of the thickness ramp. And we can see there is something happening definitely here. So let's set that to 0. Hold on there for a second and do not set this to 0. This is after I recorded the tutorial and I'm a bit wiser now. So do not set this to 0, and you're gonna see why in a second. And let's have a closer look at the extrusion. Yes, and the thing that's causing these breaks is because I didn't set it up to divide the individual elements, which I'm gonna do now. And my Houdini crashed on me. So I guess you need to give me a second and I'll be back Okay, I think I found what was causing it. So within the poly extrude sub, do not set this to 0. I repeat, do not set it to 0, but set it to something like 0.2, for example. Highlight that and reactivate it, and let's keep our fingers crossed it's not crashing on us. Yeah, exactly. And it's doing pretty much exactly what we wanted it to do. So let's get through this one more time. What I do first is, from this sphere here, which I gave an attribute of my maximum iteration, I'm just going to transfer those attributes on this regular triangular grid here and fade it out a bit so the transition is smooth. Give it a normal. And then within the for each, split the triangular grid into as many parts as I have different iteration values. And for each part, which has its own individual iteration value, ranging from 0 iterations to, in our case, 4 iterations, for each of those parts, go into this loop here and subdivide this part as many times as the iteration number tells me to. Parts with an iteration number of 1 get split into one separate piece, which then gets fed into this loop, and the subdivision is run one time on that piece. Primitives with an iteration number of 2 get split into one piece, and this piece is subdivided 2 times in here, and so on and so on. And after that, each of those pieces gets merged again and gets output here, like that. So what I'd like to do here is, again, make sure my normals are alright. Wire that up in here. And now create a curve, a spline out of it. I'm going to do that with the ends sub. And what I'd like to set it up to do is just unroll this geometry into splines, so that I have these curves here now. What I could do now in order to render this is maybe use a wireframe sub on it, or even a polywire. However, those are kind of slow as they need to generate lots of geometry, which you can see here when I hook it up. And let's make this a bit smaller, like that. And you can see I wait a given amount of time. It's not necessarily the fastest way of rendering this geometry. However, there is a more performant and more intelligent way of doing that. And let me delete those nodes. The way we're going to do it is, we're just going to create another attribute on those splines with an attribute create node, wire it up, highlight it, and what I want to create is a point attribute, which is called width, like that. And I want to set this to, say, 0.001, 0.001. Let's check. Yeah, I have a width for each point. And what I can do now when setting up the rendering is just dive up. And what I'm going to do is, in my shop network where I create the shaders, I'm going to create a hair shader. And I'm going to set it up so it's just going to be white. So set the root color to pure white and the tip color. And let's disable the blend. Maybe increase the diffuse intensity so that the white gets a bit stronger than, say, 0.5. For this case, I'm just going to disable reflections and transmission and no randomness for me, but set the opacity to be 1 everywhere. So this should just yield really solid white strands, really solid white hairs. And in the object level, just gonna create a camera by control-clicking on the camera symbol here. That creates a camera on my current viewport, position and perspective. And in the Geo node where I create all this splines, under the Material tab, I'm going to give it the newly created hair shader. Accept that. And what I want to do now is set up an environment light. And in here, just choose an HDR. For example, this one. and I'm going to dial up its intensity to say 6. What I also would like to add is a grid to have a background for these splines that we're going to render. So I'm just going to add a grid here and slightly translate that downwards like that. And yeah, I need to create a mantra node in my output dialog to configure the rendering. So I'm just going to go to rendering tab here and enable the physically based rendering. And now I think I can go to my render view and hit render. Let's see. And as you see this converging, you can see that I now have these individual splines rendered as strands with the hair shader, which is quite a nice workaround, and it saves you from creating loads and loads of geometry and instead just using the splines to render out this image. So we could call this done, but there is one tiny detail that I'd like to show you, and I'm going to stop the rendering for that. Go back into our scene, go back into the object level and into the GeoNode where we create all those splines, and just let me resize this here. And within the poly extrude, I'd like to add a thing, because when I look on those splines from the side, they just are flat and in a plane. And I'd like to give them a bit of depth, so move them a bit upwards. And the way I'm going to do it is with the distance value here. And what I could do is manually increase the distance. And in our case, it's pointing downwards, so I'll just make this negative, like that. And when I highlight that before I turn it into splines, you can see that I move those polygons upwards a bit. I could do that manually, of course. However, a neat technique that I found quite useful was again using an expression in here. And what I'd like to use for the extrusion distance is the current iteration of my for loop in here. So what I need for this for loop is another node that gives me access to its details, so something like this for the for each loop. Luckily, when I head into this node here, I can create a meta import node for that loop as well. So let's just pull that over here to make it a bit more clear what's happening there. Something like that. So this node gives me access, as you can see here on the detail tab, to the detail attributes of this for loop here. And what I'd like to do in the poly extrude, in the distance value tab here, is I'd like to access that node, and I'm going to do it again with the detail expression. Close that and give it the path to this node, so // and with autocomplete I just select this node here, then tell it which attribute to import. Let's use the iteration again and give it a default value of 0. Perfect. However, when highlighting the scene now, you can see this is happening because the values that come in here are really, really big. So it's like 1, 2, 3, 4, 5, and as you've seen here before, I inputted something like 0.005. So in order to fix that, I came up with this formula. And I'm going to take this iteration value to drive a power function. So I'm going to type pow for power, put that into brackets, and I'm going to use this detail here to power the number 2. This should make it even worse at the moment. That's because it's just increasing the number even further. I mean, if you're into abstract stuff, nice, but this is not what I was looking for. So I'm gonna use this value to divide another value. So to that side, and what I'm gonna divide is 0.01 by that. Now I can zoom in again, and this is now driving my extrusion. Something like that. Also, what I can do now is decrease the incoming value here. Let me just check. Now that's perfect as it is. Okay, so what I'm doing here actually is I take this value and I can influence that how steeply I want those extrusions to be. but I'm just going to set it to minus 0.01. And I'll divide that by 2 to the power of the current iteration number. This gets increasingly smaller as the iteration numbers get higher, and that takes care of those small faces not being pushed out too far into those other faces that have been created in a previous iteration number. And that's all this formula is for there. And if you'd like to get in-depth info about what's behind this formula, how to come up with those formulas, in-depth info on how loops works, please let us know so we can consider doing a tutorial on those details. For the moment, just take this formula, use it. Again, adjusting this parameter drives the whole extrusion depth pretty well. And let's highlight the output of that, go back into my render view and hit render again, and enjoy our image converging. Again, let us know if you're interested into more in-depth information about formulas in Houdini or about loops in Houdini. And as always, if you have any artwork to show, please do so. We're very intrigued to see what you come up with. And I hope you had fun in this. So cheers and goodbye.